So we're getting really excited about this idea of finding derivatives, of finding functions that tell us the slope of some original function. Before we get too excited and talk about some algebra rules we can use to make that work go a lot faster, we need to make sure we're not going to accidentally try to find the slope where a slope can't be found. So we have to talk in this section about differentiability. Under what circumstances can we find the derivative of a function? So big picture, an informal definition, you can find the derivative of a function anywhere it is smooth and continuous. So some places where you will not find a derivative, and there's a place for you to sketch each one of these. If there is a corner, like here, like the graph of the absolute value of x. If there is a cusp, which is kind of just a fancy sort of corner that comes when you raise your input variable x to a fraction exponent where the numerator in that fraction is even and the denominator is odd. How often does it come up? Not very often, but you need to know that at a cusp, you wouldn't be able to find a derivative. There are two more. If you think of the graph of x, the cube root of x, if you tried to make remember today in class we practiced skateboarding along these curves. So right about here, the tangent line is vertical and the slope of a vertical line is undefined. So the derivative will be undefined any place your graph has a vertical tangent. And big one, maybe like the most important part of all, you can't find the derivative of a function at a place where it is not continuous. So if you know there's a discontinuity in your function, you have to really be careful about not accidentally trying to find the derivative there. So you should have a sketch of each of these four possibilities in your notes paper now. Okay. The good news is most of the functions we study in calculus will be differentiable because most of the time our work is to take their derivatives. But you are still responsible. You, as the calculus derivative taker, must confirm that your function is differentiable before you try to take its derivative. And this is something they absolutely will test you on the AP test. Okay, so let's talk about a formal definition of when a function is differentiable. This is from your 3.1 notes, the alternative form of the derivative. Oh, that's a typo. Wow, will you fix that on your paper, guys? This should definitely say f prime of a is the limit as x approaches a of f of x minus f of x. Wow, I never caught that before. That should say f prime of a. There we go. Okay, so I'm glad we got that cleared up. Thanks. So this should definitely say f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. So that's my two x values are x and a, and I'm going to let them get closer and closer together. And here where I say both of these forms, I mean this form, which we're calling the alternative form, and the original form, which is the limit as h approaches 0. That's the one that's at the top of your 3.1 notes. They are both really important to your calculus problem-solving repertoire. So you need to know them both. But when we talk about the definition of differentiability, where or under what circumstances is a function differentiable, it's going to be sort of in this form, the alternative form, that we're going to think about our derivative. So let's try this. This is a big one. There's a place for it on your notes paper. I'm going to squeeze me out of the way so you can see the whole thing. Okay, and that is, get rid of that. Okay. So a function f is differentiable at an input a, so where the input value is a, if and only if, big picture, this says the derivative from the left is equal to the derivative from the right. We know derivative means slope, so this means, like big picture, the slope from the left has to equal the slope from the right. So there's a place for this on your important facts paper. There's a place for this on your notes paper. This one you have to know by heart. I'm going to expect you on your next test and on the AP test to use it to justify formally whether a function is or is not differentiable at a specific x value. All right, at the very bottom of your notes page, there is a little section about two theorems. One is super important, and one's like, meh. So this first one is super important. It's not complicated, but this comes up a lot. If some function f has a derivative at x equals a, then f must be continuous at x equals a. Because remember the top of the page? If f is not continuous, it can't have a derivative. So if you ever know a function does have a derivative at a specific x value, then you know it must be continuous there. And the second theorem is called the intermediate value theorem for derivatives. You can read here, this is the part that goes in your notes. If a and b are any 2 points on an interval on which f is differentiable, which means f must be smooth and continuous, then f prime is going to take on every value between f prime of a and f prime of b. So what does that mean? Since if we know f is continuous and differentiable, that means f has a derivative, which means f prime exists and is continuous. And since f prime exists and is continuous, it's a continuous function, and the intermediate value theorem must apply to it, which means that if f prime of a and f prime of b are the outputs on the f prime function, then any output that's in between f prime of a and f prime of b must exist on that function. There's a little picture here, in case it kind of helps. If I know the slope at a is 1/2 and the slope at b is 3, then between a and b, f's slope must take on every value between 1/2 and 3, which is another way of saying f prime must take on every value between 1/2 and 3. There's two theorems. The first one, super important. The second one, you could totally use it, but if you had to use it, then you could just use the intermediate value theorem on f prime, and it's not a big deal. It's not like a new thing you really have to know.